Hello, everybody. Happy Friday to you. Today, we're going to get started on a brand new unit. It's the end of the month, and we really only have about one more month left until the end of school. So, trajectory-wise, we're looking at two more units. We'll have this unit, which is all about electricity and magnetism, and then we'll have one more unit on light. You should have received your study guide by now, but if you don't have a copy, there should be extras here in the room. You just need to go up to the front table and grab one. They are printed on smaller paper than normal. That's just because I got that paper for free and I wasn't going to get charged for it. So, yeah. But still has all the same information that it would if it was bigger. You're going to want a calculator as well. You and your partner will also want a whiteboard to share between the two of you. So if you do not have any of those materials, please go get them now. If a whole bunch of you need to go get them, then the sub can pause the video so that we can go get those. Today, we're going to get started with a concept called power. We're going to learn what power is, and like we've done many times in the past, we're going to hopefully develop a mathematical model so that we can predict what the power for a particular object or situation will be. All right. We're going to start on page 4, the first page of notes in the study guide. It's titled We Are Powerful. What I wanted to do first was I wanted to show a video that I think will give us some insights into power a little bit, particularly in the context of this individual whose picture you see on page 4. His name is James Watt, and he, again, was of interest and importance in the development of this concept of power and some other things. So we're first going to watch a video a little bit about him, and then we'll have a discussion after.
James Watt was born on January 19th, 1736, in Renfrewshire, Scotland. Mostly homeschooled, he spent much of his childhood in his father's shipbuilding workshop. Aged 18, Watt traveled to London to study mathematical instrument making and eventually opened his own shop in Scotland in 1757. In 1764, Watt was given a Newcomen steam engine to repair at his workshop. Invented in 1712, the Newcomen engine operated by condensing steam in a cylinder, which in turn created enough push to power a piston. While fixing the engine, he observed that a lot of the steam was wasted due to the machine's single-cylinder design. He realized that having to repeatedly heat and cool the same cylinder wasted more than 3/4 of the steam's thermal energy. To remedy that inefficiency, Watt's design condensed the steam in a separate condenser, thus keeping the cylinder at a stable temperature. Watt's 1765 discovery greatly improved the performance of the steam engine and helped to launch the Industrial Revolution. Watt entered a business partnership with John Roebuck. The pair patented Watt's design in 1769 and started to market it in 1776. The demand for Watt's engine grew, and it was quickly adopted across multiple industries. During his lifetime, Watt received numerous awards. In 1960, the Watt unit of power was named after him. Today, all developed countries have gone through the process of industrialization, a phenomenon that the Watt engine helped to kickstart. It is for that reason that James Watt is deservedly our 13th hero of progress.
Okay. So I wanted to do a little discussion first. Let me switch back over to my iPad. Okay. Talk with your partner. What were some familiar terms you heard in that video, particularly from the unit that we just finished called Energize? I'll give us maybe 30, 45 seconds to talk, and then we'll come back together. Ready, set, go. Okay. So as I watched, some words that I recognized from our last unit included energy, work, efficiency, energy transformation, a whole bunch of the things that we just got done discussing. I wanted to quickly just refresh our memory on some definitions. Energy we have defined as the ability to do something. Work is defined as a change in energy. Efficiency, remember, is the comparison or the ratio of useful energy output to total energy input. And finally, energy transformation, well, that's really just work. That's one form of energy being transformed into another. Okay, one more question. The video also mentioned that the steam engine that James Joule created was, quote, more powerful than its predecessor. So what I want you to do is talk with your partner. What does it actually mean to you to be more powerful? Or in other words, what is power? And how does it relate to things like energy and things like work? So let's talk for a few more seconds. We'll go another 30 seconds. Talk with your partner. What does it mean to be more powerful? And what is power? Your 30 seconds starts now. All right, that's about 30 seconds. Um, in our everyday language, we use the word power quite often, and oftentimes I think it's used in the context of strength, and maybe you might have thought of force as being something related to power, and I think it probably does. You may have also heard of the word power as it relates to energy. Sorry, my lights turn off on their own. You may have heard of the word power as it relates to energy, so something that's very energetic, has a lot of power. That could also be true. What we're going to do on this page is we're going to first define what power is and how it relates to all those other terms that we're familiar with. If we start with part A on page 4, part A is a review question. It says, what are the two factors required for work to be considered done? Okay, so this was one of our topics from the last unit. If you remember the work equation reads work is equivalent to force times displacement. So the two things that need to be done in order for work to be done are we need to exert a force, and that force needs to cause some type of displacement. And really, we know that displacement was caused because these two vectors are parallel. So either in the same direction or in opposite directions. But either way, that's parallel. And so we know work was done. Part B reads, what's the mathematical model for work? Well, I kind of already wrote it down. It's force multiplied by displacement. Part C reads, what is the SI unit of work? Well, if we do the force times displacement, the unit of force is newtons, and the unit of displacement is meters, so the unit of work is Newton meters. But if you remember, a Newton meter is the equivalent of a joule, the same unit as energy. And that makes sense because work is defined as a change in energy. Part D reads, what is a rate? I think I'd like you to talk with your partner on this one. Let's just go for 10 seconds. What is a rate? Go. Yeah. So we've dealt with lots and lots of rates before. There are plenty and plenty of examples. Velocity and speed are both rates. Frequency is another rate. Acceleration is a rate, and technically so is force. Rates are defined as a change in something through time. All rates have delta something on top. and they're divided by time on the bottom, some kind of time interval. Part E says power is a rate. Power is a rate, which tells us that that whatever power is, it's going to be something divided by time. Can you guess what goes on top? Well, it turns out that power is the rate at which you do work. Power is the rate at which work is done. So to fill in our equation, power is equivalent to work divided by time. Or we could rewrite this as change in energy over time. So we can see that power and work are very closely related, but they're not exactly the same thing. Work is simply a change in energy, any change in energy. Power is more a measure of how quickly or how slowly did that change in energy occur. Okay, the next part are the units. What do you think the units for power are? Let's do the same thing we've done all year long. If power is work divided by time, the unit of work is joules. And the unit of time is seconds. So the unit of power is joules per second. Or you could also think of it as Newton meters per second. Those would be equivalent. Okay. Now, why did I show you that video about James Watt? Well, you might have picked up on it in the video. James Watt, because of his work with steam engines, we have given him a lot of credit over the years, and for that reason, the unit of power, joules per second, is also called the watt, represented by a capital W. Okay, a watt is numerically equivalent to joules per second, or Newton meters per second. They're the same thing. Okay. So down here we have a little bit of a data analysis that I wanted to try out. I'm going to fill in this part first, work over time, and the unit is watts. We got a lot of W's floating around. We have little w that means weight. We also have capital W, which means work, but then this capital W as a unit doesn't mean work, but instead it means watts. So sorry, I don't really make the rules, but it is a lot to keep track of, but we should be okay. All right, so what we're going to do is we're going to calculate the power of climbing up these stairs. This is a picture of those stairs over by the gym during construction of Ridgeline. You can kind of tell, where the walls are and all that stuff. You can see the railings. So I figured we could calculate not just the work done by climbing these stairs, but also the power. Okay. The first thing we need to figure out, right? Remember that in order to do work, we have to apply a force, and that force must cause displacement. As you climb stairs, it's very clear to see that you are being displaced. The question then is, what force is actually being exerted when you climb stairs? Well, that force would be equivalent to your body weight. Okay? So that's why right over here, it asks for weight. That's the force that we're going to be exerting. Okay, we want to first fill in the SI unit of weight. The SI unit of weight is, of course, the Newton. Okay, right over here, it says data. Okay, so we need a number to work with. I figured we could go with a very average weight for a human being. I'd say a pretty good average for most people is around 72 kilograms, but that's a mass. So if we multiply that by 10, fairly average weight for a person would be around 720 newtons. Okay. For next step over here, we have step height. Okay, so each one of those steps, I went out and measured it the other day. Each one of those steps has, actually, we should fill in the SI unit first. Height would be measured in meters. Each one of those steps has a height of 15 centimeters. So if we convert that to meters, that would be 0.15. I also counted the number of steps. The number of steps doesn't really have a unit, but the number of steps is 20. So the staircase total height, which we would measure in meters, we're simply going to multiply 20 by 0.15. So if you have your calculator, you can do that right now. But 20 times 0.5 is equivalent to 3. So by climbing these stairs, you have climbed up 3 meters. Okay, the next thing we're going to do, is we're going to record some times. Okay. And again, I did this yesterday. I went and I timed myself climbing these stairs. I tried to kind of vary it a little bit. Each trial, we're going to measure it in seconds. Okay. My first recorded trial took 10.47 seconds. My second one, I tried to go a little faster and I recorded a 6.28 climb time. And then for my third one, I tried to go kind of nice and relaxed and I ended at 12.19 seconds. All right, so this is all of our data. I think we are now ready to calculate two important things, work and power. Let's start with work. That's going to be in this first column here next to climb 1, climb 2, climb 3. To calculate work, we're simply going to use the equation that we've been using for a long time now, force times displacement. Again, what force was exerted in climbing stairs? Well, that was the weight of this person, which is about 720 newtons. The displacement is the staircase height, which is 3. So everybody in your calculator, force times displacement, 720 times 3. Hopefully you got the same number I did. I got 2,160 joules. All right. What about climb number 2? How much work was done that time? Well, it was the same because I exerted the same force and I climbed up the same height. Force times displacement is going to be the exact same as it was before, 2,160. And it should be the exact same for climb number 3. Okay? As you can see here, work does not depend on time. It's simply a measure of the force that caused something to be displaced, a change in energy. It's not dependent on how quickly or how slowly that change in energy occurred. It's just a measure of the change in energy. Power, on the other hand, is a different story. Power is defined as the rate that work was done, or work divided by time. Now I actually have to care about how long that change in energy took. So for climb number 1, we'll take the work done, which is 2,160, and we'll divide it by the time that climb 1 took, which is 10.47 seconds. So in your calculator, 2,160 divided by 10.47. Hopefully you got the same number I did. I got 206, and I think I'll just leave it at that. 206 watts, or 206 joules per second. Oh, there go my lights again. Okay, let's find the power for climb number 2. We'd have the same work on the top, 2,160 joules, but this time we would divide by a different amount of time, 6.28 seconds. So type that one into your calculators, 2,160 joules divided by 6.28 seconds. I got 340, looks like 344 watts, 344 joules per second. Okay, go ahead and calculate the power for climb 3. Do it with your partner. We'll come back in 15 seconds. Okay, I got 177 watts, 177 joules per second. Okay. Part F reads, was the amount of work done the same for each climb? The answer to that would be yes, because we applied the same force for the same displacement. Yes, the work done was the same for each climb. Part G reads, was the power done the same for each climb? And the answer to that is very clearly no. Reason being, we did the same amount of work, but we did it in different amounts of time. And that matters when it comes to power because power is a rate. H says, if you had climbed more slowly, meaning the time that it took you to climb was bigger, how would the work and power had been affected? Okay, so let's think this through. If the time it took to climb was longer than it was before, how would that affect work? Well, work doesn't depend on time. It just depends on force and displacement. So we wouldn't really experience any change in work. How would an increase in time change power? Well, we can see from our equation here that because it's a rate, time is on the bottom of this ratio. If that time value gets bigger, that would make our power smaller. And that's evidence from our data. I can see that climb 3 took the longest amount of time and it had the lowest power. So that would mean the power would decrease. And then we can make the same assumption if everything were switched. If the time that it took to complete the process were shorter, less time, again, I wouldn't change the work done, but I would have an increase in my power rate. Okay, that should conclude page 4. Okay, what I want to do now is a couple more examples with this on some whiteboards. So hopefully you already have one. If you don't, go get one for you and your partner to share. Make sure you have your calculators ready. Let's start with this one. It says the Ford Mustang is capable of doing, big number, 8,950,000 joules of work over a 25-second interval. What is the power of the Mustang? Okay, work on this one with your partner. Let's go 15 seconds, maybe 20 seconds, then we'll come back together. Okay, our power equation reads, power is work divided by time. The work was 8,950,000 joules divided by 25 seconds. I got a power of 358,000 watts or joules per second. A lot of power. Okay, let's compare that to the Ford F-150. This truck is capable of doing the exact same amount of work. So this one right over here, but it does it over a 37-second interval. With your partner, calculate the power of the F-150. Okay, should look pretty similar. 8,950,000. This time we're going to divide by 37. Okay, right away, I can pretty well tell that this amount of power is going to be smaller because the work done was done over a longer period of time. And the number I get in my calculator is indeed smaller. I got 241,891 watts. So by comparison, this Ford Mustang is more powerful than the F-150. It's capable of doing work, or I should say it's capable of doing the same amount of work over a shorter interval of time. Okay. When we talk about cars and trucks and things of that nature, you may have heard of something called a horsepower. Okay. What is a horsepower? Well, it turns out it's just another unit for power, but it's not the SI unit. Okay. It turns out that the horsepower was also invented by James Watt, but it was invented as a comparative unit to help people understand how much more powerful his steam engine was compared to older models. He compared his engine's power to the average power of a horse. Okay, so, 1 horsepower is a rough estimate of the amount of work a horse does over the course of a day on average. Okay, and you may have heard somebody say, did you know that 1 horsepower isn't even the power of an actual horse? And I think that's kind of true, but also not really. Again, a horsepower is kind of a rough average over the course of a day. Could a horse exert more power than 1 horsepower at any given moment? Absolutely. Horses can exert anywhere from 20 to 30 horsepower if they want to. but over the course of a day, the average ends up being about 1 horsepower. Okay. It's defined based on empirical units, not metric units, which is why the conversion from horsepower to watts isn't a nice clean number. So you can see here there's pounds and feet in there, which we don't really use, but that's kind of how a horsepower is defined. But for our purposes, we can see that 1 horsepower is the equivalent of 745.7 watts, or 745.7 joules per second. Let's try another one. This says an incandescent bulb, light bulb, uses 60 watts of electricity. If the light bulb is left on for 1 hour, how much energy was used? Okay, if we're going to solve this, okay, we probably ought to have a pretty useful equation, and this seems like a good use of the power equation, especially since I see the word watts written in here. So our equation looks like this, and I think this would be a good time to bring out the triangle again. If we write the triangle in its correct form, we would have work in the top and then power and time in these 2 locations. This problem is asking how much energy was used. Initially, that might seem like a problem because when I look at this triangle, I don't see anything that says energy. But remember that work is a change in energy. And if I were to say how much energy is used, that's the same as asking how much energy was changed. So really, this problem is asking for work. And so we can see that work is going to be power multiplied by time. The power of this bulb is 60 watts. The time that happened was 1 hour. But I don't want to plug 1 hour into this equation because I always want SI units. So we need to know how many seconds this is. And 1 hour is, I believe, 3,600 seconds. We need to multiply by 60 to get to minutes and then by 60 again. So we're looking at 3,600 seconds. So in your calculators, 60 times 3,600 is 216,000. What would be the units? The units here are going to be joules because we're trying to find work. 216,000 joules of energy was just expended by running this light bulb. And we looked before at efficiency, remember? Not all of that 216,000 joules was actually turned into light. In fact, the majority of it was turned into heat. But this is an incandescent bulb. These are really, really old school. You really only use them if you're looking for that kind of cool aesthetic. Most of the time, however, we are going to be using some LED light bulbs. An LED light bulb only uses 10 watts compared to 60. So do the same thing with your partner. How much energy does this bulb use in the same amount of time? 1 hour or 200, or sorry, not 200, 3,600 seconds. Sorry. Go ahead and do this one. We'll come back together in 10 seconds. Okay, so another power times time equals work application. So we have the 10 multiplied by the 1 hour or 3,600 seconds. And so that's going to be 36,000 joules. And that's a lot less energy usage. And we talked a lot last unit about how can we be more energy efficient and conservative. And really what we mean by that is how can we cut back on our usage? This is a great way to do it, right? If we do the math here, 216,000 divided by 36,000, that's a lot more energy usage, right? Or the other way to do it is 60 divided by 10. Right? We're using 6 times as much energy powering that old school light bulb. So makes more sense to makes more sense to use LEDs. All right, let's do one more whiteboard problem. This one says a 4,000 kilogram roller coaster falls from a height of 82 meters at a rate of 415,000 watts. How long did it take the roller coaster to fall? Let's first identify what we know. We have this number here, 4,000 kilograms. Kilograms is the SI unit of mass. So I have a mass. We also have this, 82 meters. That's the unit of distance or displacement. We also have this number here, 415,000 watts. That is a power measurement. It asks, how long did it take for the roller coaster to fall? It's asking us to find time. So we need to find a useful equation. I'm thinking this is another good application of our power equation, which looks like this. Our triangle setup would look like this. So if we want to find time, it's pretty clear from my equation that I'm going to need to do work divided by power. I know the power. It was told to me in the problem. 415,000. Do I know how much work was done? I don't really know. It's not off the top of my head anyway. It wasn't told to me in the problem. Is this something that we could find, though? Well, remember, work is a change in energy. We can verify pretty easily that yes, the energy of this roller coaster did change. It fell from a pretty tall height. It lost potential and gained kinetic. Could we calculate how much potential it lost? I definitely think we can, because we know the mass of the roller coaster, which means we could also very easily find its weight. That's the force that's being exerted upon it. We have a force and we have a displacement. We have everything we need to figure this out. And the force is going to be mg times delta D. And we'll divide that by 415,000. This is really the same thing as mgh, our potential energy equation. Remember, those are all the same thing anyway. So we got to plug in a whole lot of things here. We need to do 4,000 kilograms multiplied by 10 meters per second squared, that's little g, multiplied by 82 meters of displacement, and then all of that divided by 415,000 watts. Go ahead and plug that into your calculators. Let's see if we get the same thing. Yeah. As you're working, we can kind of do a little bit of a reality check. I expect this number to be, I don't know, not super big because it's a roller coaster, and roller coasters don't typically take very long to fall. Maybe, bigger than 2 or 3 seconds, but maybe not as long as like 20 seconds. That's kind of my guess. But when I plug the numbers into my calculator, I get, if we round this to the whole number place, I get about 8 seconds, which seems pretty standard for a roller coaster. 8 seconds of fall time. We can do quite a bit with this equation. Right. So to close out today, what we're going to do now is back at the end of the study guide on page 16, there's 5 think and solve problems. I would like you to do 1, 3, 4, and 5. Don't do number 2 yet. That one's probably not going to make a whole lot of sense anyway. But these are all work-related problems. Some will ask for work, others will ask for power. It's kind of that idea of how those two are related. I do have the key ready for you in my copy of the study guide. So if you want to check your answers with mine, you may do so when you're done. But let's finish this up today, and that will do it. Thanks everybody for participating. I will see you all on Monday.